Welcome to the simulation with my two toolboxes, the load flow calculation and transient simulation of high voltage networks. Today it's about the load flow calculation. Normally this is not to be done with LTSpice because the complex alternating current analysis in LTSpice is linear, but some elements in the load flow calculation are not linear. This is especially true for loads that are modeled as constant power loads and therefore do not depend linearly on the voltage. To be able to calculate nevertheless, the complex matrix system for load flow calculations is transferred in two real-life matrices. After that, the simulation can be carried out with the three nonlinear analyses in LTSpice.
These are the OP analysis, operating point analysis, to determine the working point, the transient analysis for the simulation in timeline, and the DC analysis thought for the direct current simulation, but now also best suited for nonlinear steady-state load flow calculations.
More detail can be read in the file named Mathematical Model Description .doc. There, the individual models are explained in detail. By disassembling a complex matrix into two real-valued ones, the individual elements such as the voltage source, load, overhead line, cable, and so on have twice as many connections. For example, an overhead line has now 4 connections instead of 2. 2 connections form the real part of the matrix of the element, and the other 2 connections form the imaginary part of the matrix of the element. The real connected elements have a cross in symbol O put pin to better recognize them. It is important that only the elements with a cross may be connected to each other, and the elements without a cross may also be connected to each other. Mixing is not allowed. Now to the circuit structure and the simulation. A circuit with 3 nodes is to be simulated in this example. It is assumed that the LTSpice simulator has already been configured as shown in my YouTube video and maybe even experimented a little with the surface. The LTSpice simulator was originally developed for electronic simulations, but now with my models work also very well with load flow calculations and transient high voltage simulations. I have been simulating with my models for more than 10 years and am still enthusiastic. This is also due to the intuitive handling of LTSpice, from the circuit board generation to simulation to representation and handling of the measured values, especially with the transient simulation of high voltage networks. And now for the generation of the 3-bus circuit. A template is loaded and immediately saved to a new name. Certain items necessary for the simulation are already predefined in this template. For example, the frequency is 50 Hz, the voltage factor is √3, and the power factor is 3. The voltage factors and power factor are required for single-phase simulation in order to correctly calculate the 3-phase parameters such as active power, reactive power, and voltage PQV. The parameters Vintol and Abstol are the voltage and current tolerances for the simulation, in this case 1 millivolt and 1 microampere. These values can be increased if necessary in the event of non-convergence of the simulation. The default simulation type is transient analysis for the time domain. Now let's move on to the circuit. First, we need a voltage source, which is called a slack in load flow jargon. First, we click on the IC symbol. All symbols and models, also called subcircuits, are stored here. Then we select the folder Load Flow Steady State and select the model Pretty VRI Slack 2. While placing the symbol, Ctrl E is used to mirror and Ctrl R to rotate. The voltage of this slack is set to 400 kilovolt either by right-clicking on the symbol or directly in the parameter line below the symbol. The slack ensures that the power balance of the system is always fulfilled. The sum of the energy supplied to the circuit and the energy consumed in the circuit is therefore always 0. You can see the real connection pin with the cross, the imaginary connection pin without the cross, and the 3 measurement pins on the left. From top to bottom, these are voltage measurement, active power measurement, and reactive power measurement. The voltage at the circuit output is the line to earth voltage as nominal voltage divided by square root of 3. Now I start the simulation. By clicking on the measurement pins, you can see the values for nominal voltage, active power, and reactive power. By clicking on the connection pins, you can see the real and imaginary components of the conductor earth voltage. An operating point analysis is performed before each transient analysis. If nothing is changed during the simulation in the time domain, waveform values are all horizontal lines. The values of the OP analysis correspond to the values of the transient simulation at all time values. In this case, it is also sensible to display the simulation values of the OP simulation directly in the circuit as numerical values. However, if parameters are changed in the time domain, these numerical values only apply to the simulation time t equals 0. The OP flags can be switched on and off globally. Right-click on the drawing area view, Show OP data flags. Next, we draw the bus bar for bus 1. First, I draw the bus with lines. Then I add the symbols for the bus at the top and bottom. The upper bus symbol has the phase-to-phase voltage near the cross and the voltage angle as measurement pins. The lower bus symbol has the phase-to-ground voltage measurement. I now name the bus Bus 1 with a text box. Next, I copy and name the bus twice for bus bars 2 and 3. Bus bar 3 is drawn horizontally. Now we create some space for the 3 overhead lines. Next, we get a symbol for an overhead line. The symbol is called Pretty Line Special. We open the component editor again and double-click on the Spice model line. Here we select a 400 kV steel aluminum overhead line with a cross-section of 3 by 365 square millimeters. We set the line length to 20 kilometers. This line is now copied twice and inserted further down in the circuit. We now name the lines. Next, we create a little space again. A load element is inserted at the bottom of the circuit. The load element has three modes: K equals 0 for constant impedance, K equals 1 for constant current, and K equals 2 for constant power. This is the default value. Then we change the parameter values for the load. We change the active power to 500 megawatt, the reactive power to 400 MVR, and the nominal voltage to 400 kV. We name the load Load 3. Finally, we insert another PV element and name it PV2. The PV element has a constant voltage and a constant power. To achieve the constant voltage, reactive power is added to or removed from the circuit as needed. The PV element is the second nonlinear element after the constant power load model. I now enter the parameter values. Voltage magnitude Vmag is 41 kV.
Active power is minus 200 E6, minus means the delivery.
The reactive power limits are QLO with minus 100 E6 and QUP with 0. If the target voltage has not yet been reached, the reactive power delivery will not fall below QLO. Now we connect all elements to each other. Important: only pins with a cross below each other and without a cross below each other. Then we give all measurement pins a short node piece so that we can output the measured values later. We will now assign unique names to most of the measurement pins. We forgot to name the slack, so we will do that now. The simulation is now started. The slack supplies 300 megawatt of active power and 267 megavar of reactive power to the circuit. The PV element has a voltage of 399 kV and supplies 200 megawatt of active power to the circuit. The reactive power is minus 100 megavar, which is at the limit. As a result, the desired voltage of 4.1 cannot be fully achieved. The load requires an active power of 500 megawatt and a reactive power of 400 megavar. The voltage at the load is a voltage sink of 396.8 kV. The load receives active power, and of course reactive power, from the two lines, line 13 and line 23. The value of the active power at pin P4 of line 13 is minus 266 megawatts. Since the reference arrow always points in the direction of the symbol, this means that 266.8 megawatts are supplied to the load. In addition, an active power of 233.2 megawatts is also supplied to the load at pin P5 of line 23. This results in a total of 500 megawatts. The reactive power value at pin Q4 of line 13 is minus 227.5 megavars. The value of the reactive power at pin Q5 of line 23 is minus 172.5 megavars. This results in a total of 400 megavars. The distribution of active and reactive power between the two lines, line 13 and line 23, could be changed by adding a control transformer for voltage regulation and phase regulation in series to the above line 12. If I increase the active power feed of the PV element from 200 megawatts to 250 megawatts, I also achieve a better distribution of active power between line 13 and line 23. For a better reactive power distribution between both lines, I increase the reactive power limit of PV2 to minus 180 megavar. The active and reactive power via lines 13 and 23 is now distributed approximately equally between both lines. I now look at the active power via the above line 12 and see that it is almost 0 megawatts. A few more words about the PV element. A PV element models a synchronous generator with fixed active power output and voltage regulation. The voltage regulation is achieved by changing the excitation voltage, which is accompanied by a change in reactive power. The sum of active power and reactive power results in the apparent power, i.e. the design point of the synchronous generator. I now change the PV element back to the original values for active power and reactive power limit. I am now interested in the currents over the lines. I right-click on the Waveform Viewer window and can now select the two currents from line 12. To do this, I open a second plot in the right-click menu item, Add Plot Above, and move the currents from Plot 1 to Plot 2. The current I1M is the current from the start of the line into the line, and the current I2M is the current at the end of the line. The start of the line is indicated by a small slanted line in the lower part of the overhead line symbol. The two currents are different because some current from the line still flows into the ground via the capacitances. Also interesting are the ohmic losses of the line and the reactive power balance of the line. Does the line act as a capacitor, or does the inductive component predominate due to high currents flowing through the line? To find out, I delete plot 1 and create a new plot with PVM and QVM above it. As you can see, PVM is almost 0 and QVM is approximately minus 13 megawatts. The negative sign means that the line has a reactive power surplus, i.e. it feeds reactive power into the grid. If the line were to carry more and more current, the inductive component of the line would consume more and more of the surplus. The ohmic power loss of the line is almost 0. Now I look at the voltage angle of bus 2. I see that it's negative. The voltage angle of the slack is 0. Active power always flows from the higher to the lower voltage angle. The voltage angle of bus 3 is the smallest of all 3 bus bars because the active power flows from both lines to the load. The same applies to the voltage level. Here, the reactive power always flows from the higher voltage to the lower voltage. The voltage of bus bar 3 is the lowest. Another interesting simulation results from the addition of elements with control pins. I click on the IC symbol and get a load control symbol. Now I delete the load model and replace it with one with control pins. This allows me to generate a load profile changing over time. The load now has 3 additional connections, 1 for switching on and off, and 2 for changing the active power and reactive power during the simulation. I now place short nodes on the control pins of the load and name them on PF and QF. These control pins must now be connected to the controlling voltage sources. I enter these PW equals piecewise linear voltage sources as SPICE directive, the .T symbol in the menu. I have already prepared these lines in an external editor and now paste it into the circuit. Now I start the simulation again. I output the load profiles by clicking on P-load and Q-load. The voltage profile at the load is now also changed. The same applies to the currents, e.g. via line 13, or the active and reactive powers P-slack and Q-slack. So we are now finished with this brief introduction to load flow calculation. I hope you enjoyed it. If you like, you can also take a look at the even more interesting transient simulations with my models, which include many examples. Thank you.